Okay, so since our class got interrupted this morning, I wanted to talk a little bit about what we're going to talk about, which is a little bit more about section 4.3 and also section 4.5. So we're actually in section 4.5 already, but they kind of blend into one another. And you may notice that there's 4.4 is not mentioned here. Well, we are skipping 4.4. Okay, so there's kind of a long list of things that that are our goals for this section, but principal among them, one of our main goals, okay, is to be able to identify extreme values. So this is maxes and mins, local and absolute, and identify intervals of increase and decrease, which we've already talked about that to some extent, and we want to add to this. We want to be able to ID, and you may not know what these things are yet, but we'll define them. We want to be able to identify where a function, the concavity of a function. So we need to talk about what concavity is, which we will. It's basically about the curving. And we also need to identify these things called inflection points, which are related to concavity. And then we want to kind of put all this together and be able to graph functions without the aid of a graphing calculator. And so when I say graph functions, there's kind of a lot of things that go into that, but it's all this previous stuff, like all of this. Oops, I didn't mean to do that. All of this stuff is involved in graphing functions, but also things like limits at infinity, endpoint behavior, what happens when you have a hole in the domain, asymptotes, all the other weird things that may occur. So this can get to be a pretty complicated task, graphing a function if it's a complicated function. We're not going to spend too much time on this, but this is kind of where we're going, all right? Now, there's actually some other related issues which are also really important. One of the other big things that we're going to learn how to do within this section is solving. Also, we will learn to solve optimization word problems. This will use maxes and mins. So this will be later, okay? A little bit later, not too much later, but not immediately, okay? Okay, so let's sort of recap where we are. So the big results from like 4.3 and then the beginning of 4.5. The first thing is what you see here. How do you find absolute extrema over a closed interval? And that's very important that we're talking about a closed interval AB, right? So the basic process is that you're gonna basically get your list of critical points along with the endpoints, and then you evaluate the function over all of those things. So the idea is that if it's a continuous function over a closed interval, then it has some starting point and ending point, and there's no holes in between there, so it has to have a maximum at somewhere, and it has to have a minimum somewhere. So that's what looks like the minimum and maximum here. So my picture is actually illustrative of why we look at the critical points and the endpoint, because the endpoint for a closed interval could be the max or the min as well. So what you actually do, and I mean the order that you do this is sort of you can vary from author to author, but in our text they say the first thing you should do is evaluate the function at f of a and f of b. Well, that's fine. So we evaluate f at a and we evaluate f at b and we figure out what that is, and then we get the critical points by looking at when f prime of x equals 0 or f prime of x is, let me write that on the next line, or f prime of x is undefined. Now, if you've started working on this homework for section 4.3, you'll know that getting the critical points sometimes involves some kind of fancy algebra and factoring and things like that, so you've got to be prepared for that. The other thing that should be mentioned here is, remember that the critical point must be in the interval a to b. If the critical point is not in the interval a to b, then it's not going to be, it's not worth considering. All right, so everything has to be in there. But so you get your critical points, and then you're going to, you evaluate f at a, you would evaluate f at b, and then you evaluate f at each critical point that's in AB, and then the largest of all of these is going to be the absolute max, and the smallest is going to be the absolute min. So just as it says here. And so that's the process for finding absolute extrema over a closed interval. And again, sometimes the devil is in the details. When you actually get into finding the critical points, it can be kind of difficult. So that's why you have to work lots of problems. Yeah. But moving along, the next kind of relevant question is, this is limited to a closed interval, right? So what do you do if you don't have a closed interval? What if you want to find the extrema over a open interval? Well, we have a theorem for that. It's called the first derivative test, and it is very useful. So the first derivative test, and this is something we discussed on Wednesday. If you have a continuous function over an interval I, and notice that it doesn't specify what kind of interval, but you've got an interval, continuous function over that interval and a critical point within the interval, you have to also have the condition that f is differentiable, which means f prime of x exists over the interval, except maybe at that critical point. Now, the reason we say that is because the definition of a critical point includes that the derivative doesn't exist there, so that's possible. But in any case, if all this is met, all these conditions are met, then f of c satisfies one of these three conditions. Now, what these amount to saying is that we're going to look at the sign of the derivative and use that to tell you about whether the function is increasing or decreasing, which in turn tells you whether or not you're looking at a critical or a maximum, a minimum, or neither. That's the first derivative test. And this is when the actual problem solving strategy here is outlined below. So you get your critical points, and then you cut the interval I, which I might, the interval I might actually already have a hole in it. Like, that's possible. So, because it depends on the domain of the function, right? But anyway, so you take your interval I, let's say that your interval is like A to B, open interval, and C is a critical point. Then just in this case, for one critical point, you'd look at A to C, and then you'd look at C up to B. And then we would choose a test value in each of these subintervals and calculate the value of the derivative, that's f prime. And if f prime is, depending on the sign of f prime, we can say something about f. So if f prime is less than 0, then f is decreasing. If f prime is greater than 0, f is increasing. And the only way to go from a negative derivative to a positive derivative, if the function's continuous, is to actually, in this, like from negative to positive, is actually to go through a minimum. So that means c would be a minimum, because you'd be going down and then back up. And then similarly for a maximum, if you go from positive to negative in the derivative, then it means you're going from increasing to decreasing in the function, and therefore you pass through a maximum. And then the final scenario is when it doesn't change sign. So if you don't change sign, then you don't have a minimum or a maximum. Okay, so that's a review kind of like what we did up till now. But where we're going from here is, you know, we've talked about the kind of function behavior that we've talked about is basically this. We've talked about turning points, which are another name for maxes and mins, local and absolute. And then we talked about where a function's increasing and decreasing. But that is not the whole story. There is more to function behavior than these things. So the more in-depth look at function behavior has got to include the type of curvature that the function has. And here's what I mean by that. I can draw you an increasing function like this, or I could draw you an increasing function like that. That's increasing. Or I could draw you an increasing function that did that. But this is not linear, right? Neither one of these is linear. So we need to be able to distinguish these other types of function behavior. And so this is where this concept of concavity comes into play. So concavity is sort of about the way that the function curves. And really, you know, on some level, you just have to memorize the terminology that's involved with this. So we have 4 pictures that are important for us. So let's get into that. Actually, I'm going to pause here and I'll pick this up in the next video. Okay.